typical solids for metals, as we talked about. Taking things that are either hexagonal close packed or simple cubic, body center cubic, face center cubic, and making adjustments based on how we can fit things into the gaps. Usually we think of an ionic solid as being a lattice, maybe body center cubic or something, of negatively charged particles because those are large. Right? We know anions tend to be big, cations tend to be small, so we usually think of an ionic lattice as being a three-dimensional array in which the negatively charged particles define the parts, or the bulk of the array, and the cations just kind of fit into the holes. We talked about how we can think about how to charge the different charge, how to count the different charged particles by thinking about where they sit. So an atom that sits on the corner of a unit cell only is an eighth within the unit cell. An atom in the center counts a full ion or a full particle. An atom in a face center counts a half. On the edge, so if they sit on those corners, they count a quarter. And an atom that sits in a tetrahedral hole, right? We talked about how in a face-centered array, or rather any kind of close-packed array, if I have a triangle of particles like this with an atom that caps it like so, I have a tetrahedral hole, which can be hard to visualize. The way to think of it is anytime I've got a face-centered array, you have tetrahedral holes just inside the corners. So there are 8 of them per unit cell. Right? For octahedral holes, we said they're on these edges, and we can think about how they fit in just by looking at how they fit between a face-centered array of parts. Okay? So here's an example we can look at. Right? Keeping in mind that there are really only going to be 2 types of unit cells that I'm going to ask you to think about for ionic materials and be familiar with. We'll hit them, and I'll talk about them momentarily, right? But for something like this is the unit cell for something, bless you, like lithium nitride, right? Lithium nitride is a common material. If I take a chunk of lithium metal and I put it in a pure nitrogen atmosphere, now lithium metal reacts with water and oxygen, so we have to get it away from those things. We have what we call the dry box in the lab. Right? The dry box has a recirculated nitrogen atmosphere that purifies out air and water. If I take lithium solid, lithium metal, and just leave it sitting in that atmosphere over the course of a couple of years, you'll see bright red crystals start to grow on the surface. That's lithium nitride, as the lithium actually reacts with nitrogen gas. Right? But the unit cell for lithium nitride looks something like this. In a sense, that looks like face-centered cubic. And all I've done is I've taken the face centers and I've replaced them with, in this case, nitride ions. Right? So you can see you've got the gray in the face centers and the lithiums, the pinks on the corners. Right? So how would we count those? I know that I've got 8 corners and that my lithium ions are on the corners. Corner atoms count 1/8 of an atom each per unit cell. So that tells me that in my unit cell, I have 1 lithium ion worth of volume inside the box. Which leaves me with my nitrides. My nitride ions are all sitting on face centers. Right? So how many face centers do I have per cell? 6, right? And how much do they count apiece? They count a half an ion apiece. So I have 3, yes, 3. Something's not right here. I think I have them marked backwards. Gotta be the other way around. I think I've got them misidentified. My lithiums must be gray and my nitrides must be pink. First mistake I've made all the time. All right, if that's the case, then what I have here is LiN3, and that can't be right, because nitride's -3, right? So they must be marked backwards. Check to see, that one's in your textbook. I must have marked it back. Anyway, the point being that if we now make this correct and say that my nitrides are gray, or are pink rather, have 1 nitride per cell. And my lithiums, let's make that adjustment so my lithiums are the gray ones, right? Half times 6, 3 lithium pluses. Now we get Li3N, which should be the correct formulation. Keeping in mind that we always have an empirical formula for an ionic solid. So as long as the ratio of my ions matches the formula, we're good. Right? So in this case, it's exactly the same. What we saw last time was that sodium chloride worked out, but I had 4 sodiums and 4 chlorides per unit cell, right? So there's my, wow, I completely botched that, didn't I? All right, so you have to take away about 8 credits towards my PhD on that. It should be Li3N. Never make class slides late at night. Okay, here's one that I expect you to know, because it's relatively straightforward. This is cesium chloride. Cesium chloride is a very common unit cell that we run into when your cations and your anions are about the same size. In this case, it's like a substitutional alloy, right? In the sense that I'm just going to replace one of my particles in a body-centered cubic arrangement with one of my ions. In this case, we can think of it as being the chlorides, giving us a simple cubic unit cell. And I'm going to take out of my body-centered cubic that middle ion and replace it with my cesium ion, right? Turns out cesium plus and Cl minus are almost exactly the same size. They're within about 2% of each other, and this is the arrangement they make. So one of the common unit cells that we encounter is this one, cesium chloride. I would expect that if I said so-and-so crystallizes in a cesium chloride unit cell on the exam, that you would remember cesium chloride. It's one of the few that's relatively straightforward. Right? The other one that's pretty straightforward is sodium chloride. Rock salt is the other term for that one. Sodium chloride is just the alternating plus minus array that we did in class on Monday. Right? So those two are pretty straightforward. I would hope that you can remember those two. But here's cesium chloride. That full cesium ion is in the body center. As we said, anything that's completely inside the unit cell counts a full ion towards my formula. And I've got 8 chlorides on the corner. 8 times an 8 gives me 1 chloride ion. There are 2 examples on the problem set that I ask you to count and provide formulas for Monday. Questions? All right. Since I have 1 full cesium and 1 full chloride per cell, it actually matches the formulation of cesium chloride. And I actually got this one right this time, as opposed to lithium nitride, which I completely botched and ruined my credibility. But you know, hey, it's the end of the term, and you guys know I'm not good for much by this stage anyway. All right. Questions about cesium chloride? That one's not too bad, right? And we said before, sodium chloride is one that's relatively straightforward. Take space-centered cubic and put all of your sodium ions in the gaps, in the octahedral holes, and we get sodium chloride. Again, this is an example of one, and we did this in class on Monday. For some reason, I want to keep saying Friday. We did this one in class on Monday, and when we counted our sodiums, which all sit in octahedral holes, 12 edges and 1 in the body center, gives me 4. 4 chlorides, because it's face-centered cubic. Right? So as I count them, I get the 8 corners plus the 6 faces gives me 4. The formulation of the unit cell, it's actually 4 chlorides per sodium, right? 4 chlorides and 4 sodiums rather. But a 4-to-4 ratio reduces to 1-to-1 sodium chloride, right? So a typical way you might see a problem is, hey, here's a unit cell, count all the parts and tell me what the formula of this material is, right? Remember that it needs to be in lowest terms, right? Because ionic formulas are always empirical. All right, so let's do something a little different, something new. A very common material that you run into if you ever go to one of these arts and crafts fairs, if you're one of those people who likes to do those at festivals and whatnot, sometimes they'll have the gemstone dealers who show up, right? They've got rocks and minerals and they make jewelry and all that kind of stuff. They have some of the coolest stands at some of these fairs. But you'll frequently run into fluorite. Fluorite is something that they like to sell or if you're someone who's into the mineralogy in terms of crystals and things like that, fluorides are very common crystals that they'll put on necklaces. Usually they have kind of a purplish color, and they look like, for those of you who are gamers, the eight-sided dice from Dungeons and Dragons, right? So that's kind of what fluorides typically look like. They're pretty common, right? And they're sold pretty frequently at these craft fairs by gemstone dealers, right? But fluoride has a unit cell that looks like something like this. The formula of fluoride is calcium fluoride, CaF2. And you get color by taking out periodically one of these different cations and dropping something else in that's about the same size and the same charge. Things like iron plus 2 and things like that. Putting small amounts of iron impurity is typically what gives a lot of our different gemstones their color. When we think of rubies, right? A ruby, for example, has a unit cell that's completely different, right? But what rubies are a clear, colorless array of crystalline solid called corundums, right? Corundums have a few different formulations. You get the coloration of rubies by adding small amounts of chromium in the +3 oxidation state. And when the chromiums interact with the other ions, they give the bright red colors, right? Beryl is another form of gemstone. Beryl is also colorless, but if I put small amounts of chromium in a different oxidation state in there, I get emerald. Right? So all of our different gemstones, many of our different gemstones, are just pretty plain, boring crystals that I put small amounts of the right stuff in to give them the bright colors that we observe. Right? Mineralogy itself and the study of unit cells and how the different interactions happen, and it turns out to just be crystal field theory. How the different interactions happen that give us colors are actually pretty fascinating. So, one that we run into is fluoride, this guy right here, calcium fluoride. In this case, what we're going to do is we're going to take all the tetrahedral holes, all the corners in our face-centered cubic unit cell, and we're going to drop fluoride ions in there. So this is a rare instance where we define the lattice with the positive ion, which is small, and then put large fluoride ions into the holes in the unit cell. But since every one of those fluorides sits in one of these tetrahedral holes, one of these tetrahedral gaps, where this corner right here is the corner of the unit cell, all of those fluorides lie within the unit cell. Right? So if we go back and look at our cheat sheet with the poorly done lithium nitride example here, anything that's in a tetrahedral hole must then be completely within the unit cell. Right? So we can go back then and look at our fluoride, and we can talk about how to count this guy. So for example, my calcium ions are face-centered cubic. Right? What does that mean? It means that I have 6 faces that I count half of those calcium ions each, and I have 8 corners where I count 1/8. So 6 times a half, 8 times an 8 gives me 4 calcium ions total. The fluoride ions lie inside the tetrahedral holes. Well, I have 8 tetrahedral holes. All of them are full of fluoride ions. So you can see them up there. They make a little box inside the box. And since an ion in a tetrahedral hole is completely within the bounds of the unit cell, I get 8 F minuses. So my ratio here is really 2:1, but it's inside the cell. I actually have 4 calciums and 8 fluorides. Remember that we always report an empirical formula for an ionic solid. So that matches the unit cell for the formulation of calcium fluoride. Questions about that? If we go back to our solubility rules, we remember that things like fluorides are not terribly soluble. They're one of the exceptions to our halides are usually soluble list. Fluorides tend to be things that form precipitates. And so calcium fluoride is one of these things that you go into caves or you find them around rocks and things like that, and they deposit with time And you get really nice crystals with nice faces and such. All right, questions about that? An example of tetrahedral holes and how we count them. Here's two more. Two different materials. The one on the left is something we call sphalerite. It's a typical unit cell that we run into. You talk to a mineralogist, they'll say, oh yeah, that's a sphalerite. And they'll say, oh yeah, I get that. Just like when you go to a party somewhere and somebody says, dude, you should listen to Nirvana, they're awesome. And you're like, oh yeah, I get that. And you're like, who's Nirvana? These days you might be saying that. Some people. They kind of nod and whatever along. But the sphalerite unit cell is a pretty well-known one. Not one I'm expecting you to remember, right? But we're encountering it here. It's one of two polymorphs of zinc sulfide. A polymorph, what does polymorph mean? Poly means many, morph means shape or form, right? Just like if you're an Alien fan, they call the aliens the xenomorph alien form. Anyway, I'm an alien fan. Alien's like some of the best movies ever. Polymorph means that this particular ionic material, zinc sulfide, has two different or several different unit cells that it forms. Here's one of them, right? The sphalerite form. Another one called wurtzite has a hexagonal unit cell. We're not going to even talk about that because you can't even hardly picture it. Right? But here's a unit cell for zinc sulfide. First off, we know what zinc sulfide should probably be for a formulation. How many zincs and how many sulfides relative to one another, what's the ratio of the unit cell going to have to be for this to work? It's got to be 1 to 1, right? So what happens? Well, zinc sulfide, it turns out, looks a lot like my fluoride, only I have half as many anions as I have there. So as I'm counting my cations, it's face center cubic, I've got 4 zinc ions per unit cell. What this example is, and why I'm trotting it out for you here, is to show you that you can have vacancies. Right? Meaning that I can have gaps in my unit cell just based on how my parts want to come together. So as I look at my sulfides in this structure, right, I've only filled half of my tetrahedral holes. If I fill all of the tetrahedral holes, I've got too much negative charge. That doesn't work. In this particular case, it likes to arrange those sulfides in half of the tetrahedral holes. So 4 of my tetrahedral holes are filled. And you'll also notice that they're arranged in a way that keeps those sulfides, the negative charges, as far apart as possible. Right? They're in a tetrahedron. I haven't filled up 4 on one side or 4 on the top or whatever. And it's not random. They're alternating. Right? So there's a tetrahedron of sulfides in the tetrahedral holes. Keeps them as far apart as possible. So I have 4 sulfides in here. My ratio is zinc 4, sulfide 4. Can't have that for ionic solid. We always report it as lowest terms. Zinc sulfide. How one works. Question? All right. The last one on the right, and again, all of these are in the textbook if you want to go look at them. They have other examples, including the wurtzite unit cell that I mentioned a minute ago. Now you're all just jonesing to find out what wurtzite actually looks like and how it's different. In this case, the one on the right is another common kind of unit cell. This is what we call a perovskite. A perovskite is calcium titanate. And how the individual particles fit to the cell, you can see I've mixed and matched quite a bit. I've got all kinds of different things going on with where my particles are located. And I haven't told you in this case what the formula for this particular material has to be, right? We know what calcium fluoride is, that's a common material. Zinc sulfide, we know what that has to be. Right? In this case, I've got all of these different parts in here. Calcium, titanium, and oxygen. Right? See if you can determine what the formula of this perovskite has to be based on what you see in the unit cell. All right, calcium ions are blue. How many calciums do I have? What volume of calcium do I have inside that unit cell? Well, they sit on the corners, right? 8 corners, how much does each of them count? 1/8. So how much calcium do I have per cell? 1. Just 1. What about titanium? The titanium sits in a body center, so how much of that is inside the unit cell? 1. So I have 1 ion that's completely inside the cell. So I have 1 of those. Where are my oxygens? They're on face centers, right? So if they're on face centers, they count how much apiece? 1/2. How many are there? Calcium 1, titanium 1, 3 oxygens. Calcium, titanium. This is actually a pretty common one that I'm not going to make. Questions? We have a feel for how to count things just based on where they sit within the cells. Turns out that unit cells get way more complicated than this, but these are fairly common ones, and it gives us an idea to think about how we can extend what we know about metals, right? Like what we were doing last time with chromium and whatever, or silver, to now combinations of cations and anions. Good to go. All right, so there are our answers. Last section of the course is to go back and revisit oxidation reduction reactions, things that we did back in Chem 115, and extend that now to talk about how that fits into our discussions of free energy and spontaneity. So it is the last piece to add to all of that free energy, why do reactions happen, ideas that we've been doing so far at this time. All right, so to first begin this section, we need to go back and kind of review a little bit about oxidation reduction. What we're really going to be talking about is what force, right? Not that all-seeing, all-powerful, mystical force Han Solo talks about, but what force is pushing electrons from one place to another. That whole idea of that force, or electromotive force, EMF, is measured in what units? How many people remember from physics way back, probably in high school or earth science? EMF, electromotive force, is unbelievable low. For people who like 90s music. No? See another reference that people are like, oh yeah, I get that. I'm used to it from old. EMF, electromotive force. No, coulomb is the unit of charge. A joule per coulomb is also equal to this. When you plug in a battery, right, what does it say on the side? Volts, right? So we're going to start talking about voltages. Or another term for that is potentials, right? What's pushing things around? I don't like the term potential because it implies when people use it on people that you're not doing very well, right? You have great potential. And at the same time, you're going, yay, and you're also going, screw you. So, when we talk about oxidation reduction reactions, we're talking about stuff like this. These are kinds of reactions that we use to lay the groundwork for how electrons move around. We used to do this particular reaction in lab, right? We used to have what we would call our atomic reactions lab type thing. And we did a whole bunch of demonstrations, and people would watch and write these things down. We take sodium and chloride and we put them together inside of a bulb, and you just let them rip. And what happens is you get a big flash, and lots of sodium chloride comes snowing out of the atmosphere, essentially. The sodium and the chloride react, right? There's enough reactivity between the two that the solid reacts directly with the gas and makes our sodium chloride. This is a reaction that we're used to seeing, right? And we have a good idea for what happens in this reaction. We can separate it into the two parts. We have sodium, which is taking, and it's giving an electron away to chlorine in order to make sodium ions. The chlorine absorbs 2 electrons, because I've got Cl2, and becomes chloride ions, and we make sodium chloride. And what we see in this reaction is when we separate those into the two parts, we can actually bookkeep where the electrons are and how they go from one place to another. Our sodium is providing electrons to the chloride, which is absorbing the electrons. And the one thing that we notice about this process also is that in order to make the reaction balance, we know we can balance mass by putting a 2 in front of the sodium and in front of the sodium chloride. We usually think about that as balancing mass, but what we're really doing is also balancing the electrons that are relatively unseen in the background. It turns out in this case, when you balance the mass, you're balancing the electrons at the same time. It's not always true, right? So that's part of where we're going next. But in order to make this reaction go, I need sodium to provide electrons twice. I need, for every chlorine, 1 sodium to react with each chlorine atom. Chlorine comes in pairs, so I need 2 sodiums. Again, we balance the mass, we see that part, but we're also balancing the electrons. And so the last part of balancing chemical equations that we talked about back in Chem 115 is this idea of looking for the electrons, where they are, where they're going, what's their source, and where are they consumed. So we have 2 opposite processes. We have the absorption of electrons by chlorine, we have the release of electrons by sodium over here. And when we think about how we've separated those, we've essentially created 2 opposite processes, or we have 2 half reactions within that overall reaction above. So when we talk about half reactions in electrochemistry and oxidation reduction reactions, we're talking about the fact that I have 1 process that creates electrons and 1 process that consumes electrons within the entire process. Right? So all of that stuff is going on at one time. Right? So this idea of half reactions is separating my overall oxidation reduction reaction into these 2 parts, one where they're being produced electrons and the other where they're being consumed. Right? So, takes us to the terminology. Oxidation, remember from Chem 115, an oxidation is a process that releases electrons to the surroundings. Right? It's something where we're giving away electrons, or if I write a half reaction, my electrons are on the product side. So as I'm doing this process, right, I'm giving away electrons. Something is becoming more positive. Right? The way we think about it in organic chemistry is really where the term comes from. It's an archaic term. By archaic, I mean like 200-300 years old. The adding of oxygen. Right? When I take something and I add oxygen to it, we know oxygen likes to be negatively charged. Whatever you're adding that oxygen to must be becoming more positively charged. Right? So that idea of oxidation is raising the charge, making it more positive by adding oxygen. That's where it came from. Or we can think about it as just something is becoming more positive. Sodium is going to sodium plus. It's becoming more positive. Right? Reduction is exactly what it sounds like. I'm reducing the charge on something by adding electrons to it. The electrons are in the reactant side of my equation, my half reaction, and they're being bound to something that makes it more negative. Right? So our chlorine is absorbing electrons and becoming more negative. The other way to think about it again, electrons are on the reactant side. Right? For a balanced reaction to occur, I can't put 2 reductions together because I have 2 individual parts that are requiring electrons, or where electrons would go on the reactant side. I have nothing that's powering one versus the other, and that's how you can think of this. My sodium is powering the half reaction of my chloride. Right? This is providing the fuel for this to occur. So however you thought about half reactions and however you thought about oxidations and reductions in Chem 115, it still holds. Right? We're just going to go a little bit further with it than you did before. So you can actually take this. It turns out that if my link here no longer works directly out of my presentation, otherwise we'd watch it. But the silver tree reaction is a pretty common one that you'll run into. It's a demonstration where you take a silver solution, silver nitrate, and you put a coiled up piece of copper wire in there, or sometimes what they'll do if you watch the demonstrations online is they'll shape the copper like a Christmas tree, and they'll drop it in there, and what happens is that the silver will slowly go from silver plus ions in solution to silver metal, which is what we see in this particular balanced equation here. The copper is slowly dissolving and becoming copper ions. Your solution turns blue, and you get this silvery, tinsely stuff that deposits on the copper wire. Right? And after a little while, it just turns into mud. But for the first portion of the reaction, it's really kind of cool. Right? And you can go and you can look at that. That's one example. That when I plugged it into a browser separately, it still worked. Right? But it doesn't seem to work on my presentation, so I can't show it to you. But the balanced equation is up there, right? Or at least a partially balanced equation. Because I can do the same thing with this reaction that I did with sodium and chlorine. I can separate it into its two parts. What I've done here is I've removed the spectator ions. What you notice is nitrate doesn't do anything in this reaction, right? Nitrate is just there to be the carrier for my silver ions, right? And it's the partner then for my copper ions after the reaction is done. So it's just a spectator. But as I look at what happens, this actually looks fairly similar to the half reactions we looked at before. I have one half reaction that involves 2 electrons and another half reaction that only involves 1. In this case, my oxidation is releasing 2 electrons, and my reduction is only taking them 1 at a time, right? So my silver is powered, I can power that twice by having 1 copper react. Some of us remember some of the different mnemonics we use to remember oxidation and reduction from either 115 or high school or whatever. Some people did Leo says Ger. How many people know Leo says Ger? Right? Lose electrons, oxidation, gain electrons, reduction. Right, that one. Or oil rig. Oil rig's the one I learned back in the day. Oxidation is loss of electrons, meaning they're on the product side. Reduction is gain. Right, so we can see our silver is gaining electrons. It's becoming more negative. That's my reduction. Or the other way to think about it is my electrons are on the reactant side. Reactant side means reduction. Oxidation is on the product side over here for my copper. So I can separate my parts, a single reactant and a single product going together into one half reaction over here for copper. And the same thing is true over here. I can figure out how my individual materials are changing based on this reaction process. Right? All of this should be reviewed. Right? If this is not reviewed, come see me on office hours, we'll talk about it. But you should have done something like this in Chem 115. Questions? All right, so how many times can I power that silver equation with the copper equation? I can do it twice, right? So in order to balance the overall reaction, there we go, I can double the silver and get the balanced equation to work out. Again, we're balancing electrons, but we don't see the electrons because the electrons cancel, right? Every electron that is produced by copper is consumed by silver, and in a sense, it's like Hess's law. When I add the equations together, I can cancel the electrons. A couple other terms that we run into, and this is what people find confusing, is that we can call one material the oxidant, right? The oxidant is the agent that causes the oxidation to occur, right? ANT means sort of like this agent or the cause of something. The confusing part is that the oxidant is in which half reaction? It's in the reduction, right? So based on how the terms were originally developed, right, that idea of the agent that causes oxidation means that it has to be in the other half reaction. It's in the reduction. The reductant in this case is copper. It is the thing that's causing the reduction to occur, the agent of reduction, right? And it is found in the oxidation. So copper is our reducing agent. It's the thing giving away the electrons. And silver is our oxidant. It's the thing taking up electrons. And again, they're found in opposite half reactions, which messes with people a little bit. Questions on that? How many people remember learning this in 115? How many people are just raising their hands because they want to look like they were too smart? How many people absolutely refuse to raise their hand at 9 times wrong? 9 of them. All right. All right, so at this stage, we moved over to what we call oxidation numbers. Oxidation numbers are those charges that allow us to keep track of where our electrons are within materials. They're different from formal charges. Remember, formal charges are based on Lewis dot structures, and Lewis dot structures are where we move those electrons around in those resonance structures, and we figure out how positive or negative an atom feels based on how I've arranged my bonds, right? When we look at oxidation numbers are a way to keep track of electrons by treating just about everything like an ion. So in a way, it's the same kind of idea. We want to see how positive or negative atoms feel, but we're going to come at it from an ionic perspective. as opposed to coming at it from a covalent shared electrons loose structure perspective. Most of these rules, you know, this comes out of the blue text. It's also in the Gilbert book in chapter 17, but it comes out of the blue text, the Rayner-Cannon book in section 8.2. Things like, first off, we know that the oxidation numbers all have to add up to the total charge of the species. All we're really doing when we do oxidation numbers is trying to figure out, relative to neutral atoms, how many electrons I've moved around and where they are, right? So we're always balancing protons and electrons when we calculate oxidation numbers. They need to always add up to whatever the overall charge of the species is. We treat elements as having a charge of 0, right? That's something else we do. Hydrogen is almost always +1. It's only -1 when we bind it to metals, which are less electronegative than hydrogen, right? So when we look at that fight over electrons, positive versus negative, a less electronegative species is more likely to give electrons to hydrogen and make it look like a hydride, a -1. Whereas something that's more electronegative, like carbon or oxygen or nitrogen, tends to drag electrons away and make the carbon or the hydrogen look like a proton. Alkali metals are always +1. Beryllium group is always +2. Fluoride is -1, our most electronegative element. Always carries a -1 charge unless it's F2. Right? Oxygen is always -2 unless we bind it to F, which wins the electronegativity battle, right? Or unless we bind it or make this peroxide ion O2, 2-. We don't run into a lot of peroxides, but they're out there. Halogens are usually -1 unless we bind them to O or F, or a more electronegative halogen. So bromine loses to chlorine. Chlorine will be -1, and bromine will have to deal with whatever it gets. And our chalcogens, the oxygen group, follows the same general pattern. After that, we don't have a lot of rules, and we tend to apply these in order, and it allows us then to determine what we're looking at for these different species. There we go. So we've used this before. We used the same kind of an idea when we were calculating the charge of a metal in a coordination complex, right? We figured out what our overall charge was, assigned oxidation numbers to what we knew, and then derived the charge of the metal as a result. So we can take something like phosphate in this case, and we can determine, or rather phosphoric acid, we can determine the oxidation number, the charge on a phosphorus atom in phosphoric acid by following our rules, right? First off, we know that the overall charge in phosphoric acid is 0. There's a 0 up here, right? So all of our oxidation numbers for hydrogen, phosphorus, and oxygen must add up to 0 when I'm done, right? Hydrogen is +1 when attached to nonmetals. We know in an acid like phosphoric acid, our hydrogens are bonded to oxygen, so they're going to be +1s. So I've got 3 hydrogens at +1 apiece. I don't have a rule for phosphorus, but I can assign a number to oxygen based on our rules. As I follow down through, I get to oxygen and it says it's -2, but I don't have F and it's not peroxide, so it's got -2. I can do the math and see that my phosphorus is +5. And when we think back to how our oxidation numbers work, when we look at something like phosphorus, we know that phosphorus wants to be -3 or +3, right? Or I can completely vacate the valence shell and it can be +5. So that number actually makes sense, right? So our math is internally consistent with what we already know about the periodic table. Questions about that? All right. Dichromate is bright orange stuff. Right? We use it as an oxidant in organic chemistry. It's something that we react with things like aldehydes, and dichromate, I think, turns aldehydes into carboxylic acids. Right? So we further oxidize them. What is the oxidation number of chromium in dichromate? Well, we follow our rules. I know that whatever those oxidation numbers for those elements adds up to, it has to be -2 when I'm done, right? So that already tells us about the balance of protons and electrons. I don't know what chromium is, but I got 2 of them. So I'm going to have 2 chromiums in my relationship here. And I have 7 oxygens at -2 apiece. So -2 is equal to 2 chromiums plus -14. 2 chromiums equal plus 12. The charge on chromium is plus 12 over 2 equals plus 6. Now, keep in mind, this process just gives you an average oxidation number because it has nothing to do with the actual structure. It's just looking at the formula and saying, how do I organize the pieces? We know in something like some kind of an organic molecule, like maybe acetic acid or something like that, that if we calculate the oxidation number of the carbon in the methyl group, it should be different from the carbon that is in the carboxylate group, right, in acetic acid. Right? But if you were to calculate that value, you would end up with an average between the two by this method. Right? So that's really all we're getting here is an average oxidation number for chromium. In this case, they turn out to be +3 or +6 rather. Questions about this method? We've used it in a couple of other different places, but it asks you to go through all of those rules. Again, just looking mostly at the charges we just assumed from the periodic table. All right. Okay, so with that in mind, we can look at an equation like this, where we take methane and we burn it, and we can determine what is being oxidized and what is being reduced, and we can determine what the oxidant is and what the reductant is. So, the easiest way to go through this, or the most exhaustive way to figure out what's going on in terms of what's being changed, is to assign oxidation numbers to everything in the equation, right? And see what is becoming more positive and what is becoming more negative. Well, it's easy to tell what's becoming more negative, right? What is absorbing the electrons? What is my oxidant in the equation that has oxygen in it? Right, my oxygen. So if I look at this guy, this is elemental oxygen, starting out at 0, and based on our rules, it's going to -2 and all of these other compounds over here. Okay. What about my hydrogen? Hydrogen is always +1 unless I bind it to a metal that's more electropositive or less electronegative, if you prefer. Right? Am I binding it to a metal here? No. So that means that this hydrogen is going to be +1. What about over here? What's my oxidation number for hydrogen in water? If my oxygen's -2, my hydrogen's got to be +1 also. So is anything changing for hydrogen in my equation? No. Which leaves one last thing that's going to have to change if this is going to be changing charges, right? Carbon on the left has to have an oxidation number of what? Got to be what? 4 plus or minus? It's got to be -4, right? So my carbon starts out in a place where it's, by this method, relatively electron rich, right? It's feeling like a charge of -4. What does it turn into on the right? +4. So if I look at my overall reaction, which species is being oxidized, right? Which species is becoming more positive as I go from the left to the right? Right. Now keep in mind, I can't separate the carbon from the methane, right? So in this particular species, methane is the thing that's being oxidized, right? We know the carbon is the fundamental part of that that's actually losing the electrons based on this method, right? In reality, we know that methane is a covalent molecule and it's going to do all kinds of weird things. But what it says is my source of electrons in this is my methane. Right? So methane is my species that is being oxidized. What's being reduced? Oxygen is being reduced. So if I look at where my half reactions would go, my oxygen actually goes into two different species, but my carbon goes here. And I can see there's an 8 electron change for my carbon. My carbon's going from -4 to +4. My oxygen gets spread out over lots of stuff, but my oxygen's all -2. Right? So then the question is, my carbon is being oxidized. What's my oxidant? That's right. Oxygen's my oxidant. That's the easy one. Right? Anytime you see O2, almost any time, it's going to be taking up electrons. It's going to be in the reduction half reaction, absorbing electrons, and it's going to be my oxidant, which means my reductant, the thing being oxidized, is methane. A and T should tell you that we're always, when we identify oxidants and reductants, looking at this side of my balance equation. This is exactly this balance. And it looks like it's balanced. This side is where I find those parts. Right? CO2 is not my reductant. CO2 is a product. So when we look at oxidants and reductants, we're always looking at the reactant side of the equation. All right. Questions? All right. Now, when we balance oxidation and reduction reactions, we can have some like the ones we looked at earlier, which we can do by inspection, right? What does it mean to balance by inspection? When you inspect something, what are you doing? You're looking at it, right? Or balancing by inspection means by trial and error, pretty much, right? You change the numbers a little bit until you get everything to work out, and everyone's happy, and you turn it into paper, and you get a smiley face, right? So that's how we do a lot of these, but we get to the one on the bottom. Here's a net ionic equation that happens in aqueous solution. You've done permanganate. Your lab used permanganate and oxalate, right? In this case, we're going to use iron instead of oxalate. You can't balance that equation, right? When you look at it, you can't balance it. And you can try, it won't work. Part of the reason why you can't balance it is, I've got no place to put all my extra oxygen. When I look at the left-hand side, my manganese, I've got one on the left, one on the right, and all of my oxygen is all associated with manganese in this equation. You can't balance that. And the key idea is, with this, that very frequently, when we're balancing reactions that happen in solution, my water, the solvent, is non-innocent, right? Non-innocent means it's participating in my reaction. So we already know that water does this all by itself. Water auto-dissociates into H3O plus and OH minus. So anytime I do a reaction in water, I have some of these other things present at the same time. And we know that acid, H3O plus, and base, hydroxide, are pretty reactive species. What we're not seeing is the participation of water in some of these reactions that occur in aqueous media. So we're going to look at a method that helps us to bookkeep electrons as they move back and forth in some of these more complicated oxidation reduction reactions. Okay? So I know my class back in 115 looked at the half reaction method for how to balance oxidation reduction reactions. I know that the other Dr. Doffey's class looks at them some. So for some people this will be review. For other people this is a whirlwind tour probably of how this is done. Right? But how do we figure out how water participates in an oxidation reduction reaction? Well, we have a set of rules that really expand what we did before with sodium and chlorine, right? That really expand all of those steps that we did before to account for how water can participate in these reactions. And all of these steps are in the book, right? They're in section 8.6 of Rayner Canham and in 17.1 of the Gilbert book. But what it does is it says, when we look back at what we did here, right? Go all the way back to this guy, which now everyone's mad because you were all scribbling down all the stuff. we took this reaction, right, we broke it down into its two parts. So we identified the species that had to go together. We looked at where the electrons were. Which one is making electrons and how many? Which one is consuming electrons and how many? Right? Made the electrons balance, right? We put a 2 in front of silver, and then we put them back together into an overall equation that was balanced. Right? So, took the equation, broke it down into its parts, identified the number of electrons, made the electrons the same so that it would balance, and then put them back together. All we're going to do in this process is add water into that mixture, right? And how water impacts how those parts come together. So that's my attempt to try to make this seem less obvious. But it takes space and time to do this. And there is one on the problem set. So in this case, we have our reaction of permanganate and iron plus 2 going to manganese 4 oxide. This turns out to be a solid, and iron 3 plus. So the first thing I need to do is separate this into 2 half reactions that allows us to keep track of our parts. So what we should identify is the fact that in order to balance anything with manganese, I have to have manganese species in one of my half reactions. Those things have to go together. And in order to figure out what's going on with iron, these two have to go together as well. Now the nice part about this particular problem is I can balance this part right off the bat. Okay. I can see that my iron is being oxidized, becoming iron plus 3. So the manganese must be the thing that's taking up electrons. We've got to figure out how that works. So the first thing I do is I look at my half reactions and I check everything that's not O or H, because I have the ability to balance hydrogen and oxygen using water. Everything that's not O or H, I check to make sure that it's balanced. So if I look at this guy, my manganese here, I have 1 on the left, 1 on the right. All it says is check everything that's not O or H and make sure you got the right numbers. So I'm okay with that. So that's second part after I break it down in half. Now I'm going to look at this and say, okay, the problem I have is I can't balance my oxygen. That's why I couldn't balance this by inspection. So I need to involve water in some way. So I look at this reaction and I say, what is my problem? Well, I have lots of problems, but my problem with this equation is that I've always got too many oxygens over here. So what I'm going to do is I'm going to balance my oxygen by adding water. Essentially what it says is that if I follow my steps, I can use H2O, H3O plus, and OH minus as I need them to help my equation balance. So now what I've done is I've made sure my manganese works, and I've made sure my oxygen works, but by doing this, I've introduced what that doesn't balance at this stage? Hydrogen doesn't balance. So the next step is, well, I have access to H3O plus. I'm going to simplify this down and just say H plus, because if I add H3O plus, I got to go back and add some extra water, and I don't want to unbalance any of those things. So how many hydrogens do I have on the right here? I have 4, and I don't have any on the left. So what my method says then is to add enough acid to make sure that all of my hydrogen ions now balance. So I balanced everything that was not O and H first, then I balanced O by adding water, and I balanced H by adding acid. Question. All of those are present in my water equilibrium. Now what? Well, the only thing that's not balanced in this half reaction now is the charge. Right? I haven't accounted for electrons. Over here, I've got 4 plus 1 charges, and over here I've got 1 minus 1. So the total charge on this half of my reaction is plus 3. Over here, my manganese oxide has a charge of 0. I have 2 waters with a charge of 0, so my total charge on the right is 0. So those two half reactions, two sides of the half reaction, sorry, balanced by how many charge units, or how much do they differ by? 3. The left-hand side is 3 electrons more positive than the right-hand side. What does that tell me? In order to make them the same, I have to reduce the charge on this side so that it's the same as the other. Right? What did I do over here? I looked at this and I said, oh, my right-hand side is too positive by 1 charge unit. So I added 1 electron to the right-hand side to make them the same. Same idea over here. This is now a fully balanced half reaction. That's a fully balanced half reaction. In essence, we've reached the stage where we were back here, going back. Here we go. Where I've added the 2, or figured out the number of electrons before I've added the 2. The last step in the process now is to make the number the same, trying to figure out what number in red I need for these 2 half reactions to make this work. In other words, I'm saying this half reaction requires 3 electrons, but this one only makes them how many at a time? 1. So how many times does this half reaction have to work to power that one? 3. So I need that half reaction to go 3 times in order to make this one go once. So now I can recombine them and figure out what my overall reaction looks like. So my first half reaction on the left, 3 electrons, 4 H pluses permanganate, going to MnO2 and 2 waters, is powered by this reaction that happens 3 times. So now I have 3 Fe2 pluses. I have 3 Fe3 pluses and 3 electrons. So just like with Hess's law, I can add these together. What's going to cancel? Electrons, they must. If you have electrons left over when you're done, that's a built-in check that tells you you did something wrong. But I have 3 electrons on the left, 3 electrons on the right. So my overall reaction is I've got 4 hydrogen ions reacting with 1 permanganate and 3 iron 2 plus ions to give us a manganese 4 oxide, which is a solid, 2 waters, and iron 3 plus aqueous 3 O. That should balance, I hope. Keeping in mind, the only thing we added were the water, the OH steps in the middle, that's different than this. Part of what we have to deal with the fact that water is something that does a whole bunch of stuff by itself that can impact how chemical reactions occur. We almost always balance these as net ionic equations because it's much easier than dealing with all the extra chlorides or sodiums or whatever else you might have in there that don't change. So, questions about these, what we did here. We'll do another example on Friday and then start moving into the idea of how do we figure out what force is actually pushing the electrons from one side to the other.